Hello, my name is Casey Silva, and I am a master's student within the School of Biological and Health Systems Engineering here at ASU. This video is an introduction to my applied project, which I completed within the Spine Biomechanics Lab at Bayer Neurological Institute under the direction of my mentor and committee chair, Dr. Brian Kelly. The completion of this project was also made possible through the support of my committee, Dr. James Abbas and Dr. Vincent Pizzicone. My applied project entailed the validation of an optical strain mapping system using an in vitro model with application to implantable spinal instrumentation.
There is a fundamental relationship between stress and strain. Strain is a direct indicator of stress and is often measured when characterizing materials. Traditionally, strain is measured with mechanical strain gauges. Strain gauges are limited because they only provide point-wise strain measurements, and they are not always easy to bond to a surface. They are especially difficult to bond to non-homogeneous surfaces such as porous bone or striated moist tissue. Digital image correlation, or DIC, is an optical strain measurement method which is capable of comprehensively measuring strain distributions on non-homogeneous surfaces by tracking deformations in surface speckle patterns. This makes it an ideal tool to use when analyzing tissue, or tissue instrumented with a supporting construct, such as the cadaveric test models used by the Spine Biomechanics Lab, as can be seen in the pictures on this slide. To assess DIC as an instrumentation method, we performed a set of analyses to investigate different aspects of the system, including comparisons to the gold standard in strain measurement, mechanical strain gauges. 4 aspects of our system were assessed: the effect of speckle pattern on overall data quality, the baseline noise of the system over a few different loads, the repeatability of DIC measurement across different calibrations, and the accuracy of DIC measurement as compared to gold standard mechanical strain gauges. Finally, we used the DIC system to take a first glance at some rods that were bent via 2 different mechanical methods. We sought to identify any interesting strain distributions at locations of interest, or make any comparisons between the different bending methods in terms of observed rod strain. To carry out testing, a physiologically relevant standardized model used to evaluate the strength and fatigue life of spinal rods, ASTM F1717, was used. Uniaxial strain gauges were placed at standardized locations on the top and bottom of each rod. Rods were then speckle coated for DIC and analyzed during flexion and extension via MTS hydraulic frame testing. DIC data was analyzed and strain distributions were generated and superimposed over the corresponding 2D images for each test. DIC allowed for the use of different virtual tools, although we will focus on the extensometer and area tools in this report. The selections for the extensometer and area tools, which can be seen on the right, were virtually placed over the mechanical strain gauges at the top and bottom of each rod. To summarize the scope of this project, several parameters regarding the DIC system's accuracy, precision, and reliability were assessed. To achieve this, an in vitro model with application to implantable spinal instrumentation was used to test the system. Please join me at my symposium Zoom session for more information about my project, including an in-depth description of my methods, test results for each assessment, an analysis of the effective bending method on rod strain distribution, and overall conclusions. Thank you very much. The Zoom link and meeting ID can be seen below. They are also provided in the description of the YouTube video. I look forward to seeing you at Symposium.